Hi, welcome to this lesson on similar shapes. We've learnt a little bit about scale factor and enlargement and reductions. We've also been looking at how to calculate dimensions or sides that we didn't know the value of using scale factor. I want just to have a look at one aspect or one type of problem that we might come across. These are two kind of typical diagrams that we might find, and in this lesson we're going to have a look at what I call the double triangle. I think it's more formerly known as the overlapping triangle, but I like double triangle because we're dealing with shapes like this. It's one of those puzzles, which is how many triangles can you see, because of course there's the big triangle on the outside, and then there's, because of this one line, it actually makes a small triangle on the inside. Well, it's an interesting application about similar shapes, because if these two lines are parallel, then we can use the idea of F shape or of corresponding angles to judge that in actual fact, see there's the F shape there. It tells us that these two angles are equal, and there's an F shape on the other side here, which means that these two angles are equal. And of course this angle here is common to the small triangle and the larger triangle. So in actual fact, if we were to think about it like that and pull them out, we'll pull out the X goes in that angle, the tick goes there, the circle goes there. Do you notice that in actual fact we have two triangles that have matching angles in each of their vertices, which means they are similar shapes. So we've got, by making one of these double triangles, we're actually making a pair of similar shapes, and we can work out stuff from that. And usually it's good, as I've just done there, to separate the two shapes, to actually draw them as two distinct shapes and not work on them together in the one. So that's what we're going to do with these. Let's have a look at example 1. Calculate the value of x. So x is the length of the base of this triangle, and there's various dimensions. This line going across the middle is 8 centimeters. The top part of the line is 6. The bottom part is 3 centimeters. Now the important thing I would do is I would redraw the shapes. So I would maybe draw the large one on its own. I'll maybe put it over here. It doesn't have to be, let's not make it a dotted line. It doesn't have to be exactly the same size, as long as you're happy with the fact that they should look kind of, I'll make this one a wee bit smaller. So here we've got two triangles. And I'm going to write in the dimensions that are appropriate for each one. So in the large one here, that's x, and this is 6 add 3. So the whole side there is 9 centimeters. Okay. Now the small one here is the top triangle here, which is 8 centimeters along the bottom, and it's 6 centimeters there. Okay. We're now in a situation where we can use the skills that we were learning in the previous lesson in order to work out x. So what we can do is we can establish the fact that we've got a matching pair of sides. X is in the larger shape, so we're actually going to work out an enlargement scale factor, which tells us we need to create a fraction which is bigger than 1. So we're going to make a fraction bigger than 1 with the numbers 9 and 6. Which one goes on the top? If it's an enlargement scale factor, the big number goes on the top. If it's an enlargement scale factor, it needs to be bigger than 1, in which case you need to make an improper fraction. Whatever kind of works in your head to make the correct fraction. We've got 9 over 6. That simplifies. Divide through by 3 to get 3 over 2 or 1.5, depending on how you need to proceed with a calculator or without a calculator. Either of those is fine. It means that x, the actual dimension we're trying to find, is going to be connected to its matching side, which is 8. So 8 centimeters multiplied by the scale factor. So x is 8 multiplied by 3 over 2, or 1.5. So 8, remember you can multiply the whole number by the numerator there. 8 times 3 is 24, divided by 2 is 12, or you could do 8 divided by 2 is 4, times 3 is 12. Either way you get 12. centimeters, and there is the value of x. We've answered the question. Okay, let's look at example 2, because depending on where x is, it can get a wee bit trickier. So let's have a look at this one here. We've got our shape here. Now the key thing about that, the line in the middle, it's got to be parallel to the line outside, otherwise the shapes are not similar. Okay, so let's draw the two shapes. I think for time, I think I'm going to just do this, except that, okay, what I need to do, you're going to draw it totally, but remember there's a 12 here, plus x, okay? So what we've done here is we've got a 35 centimeter line, and the base here was 12 centimeters and x, so I have to put a wee plus sign in there for the length of that line. We've got 14 and we've got 12. Okay, so as always, these are similar shapes. We've got 35 and 14 are our matching sides. The x is again on the large shape, so I'm going to make an enlargement scale factor. Make a fraction. What have I got? 35 and 14. If it's an enlargement scale factor, the big number goes on top. Make a fraction bigger than 1. That's not going to make a very nice fraction, so I'm just going to make a decimal fraction out of it. 35 divided by 14. Oh well, it will. Oh well, I was not clued up there. 2.5, I could have divided through by 7, couldn't I? You were spotting that, 5 over 2. There we go, 2.5 or 5 over 2. So what are we doing now? Here the problem is that the side, the x is not a side on its own. We can't just write x equals, okay? So in this case here, we write down the dimension of the side that's got the x in it, which is 12 plus x, or x plus 12. Let's do x plus 12. So that side here, just as though we would normally do it, it's the, well, the problem is we've got 12 centimeters here. So I'm going to rewrite that so that to avoid confusion. What we normally say in this case, because it's an enlargement scale factor, is that if we multiply 12 by the scale factor, then we're going to get 12 plus x. So let's redo that. So the side that's got x in it is 12 plus x. And in order to get that, we would take our 12 centimeters and we'd multiply it by the scale factor. So in other words, 12 plus x is 12 multiplied by 2.5. 12 plus x is equal to, well, 2.5 times 12 is 30. So this time we haven't worked out x is 30, we've worked out 12 plus x is 30 because we have to keep the length of the whole side. So what do? Solve a little equation, take 12 away from both sides, or just use your arithmetic. 12 add what is 30, x is 18. So in this case here, x is actually 18 centimeters. So a little bit of algebra helps, and that's why we do have to think about formal ways of solving these kind of questions sometimes. Okay, last one. Calculate the value of x here. So just very quickly, I'm going to draw the shapes out. We have to think about this. We've got let's do the small shape here, and then we've got the large one here. Okay, so let's look at what we've got to fill in. We've got x on the small shape, and we've got 6, and we've got 24 on the base here. They're all centimeters. And this one here, the long side of the outside is x plus 9. Now this shape here has x's on both triangles. Does that make it different? Well, we can still use algebra, and that's fine. The key thing is we have got a matching pair of numbers, so we can work out the scale factor. This time, because we think, well, we think about where's the x, what's our new shape, it doesn't really matter which is which, okay? So we can either find an enlargement or a reduction. I'm going to go with the idea of the x plus 9 being the larger one, okay? This makes kind of sense. So we'll say that the enlargement scale factor, as always, is the bigger number over the smaller number. Make a number bigger than 1. So enlargement scale factor is 4. That means everything here is 4 times the small one. So In order to construct this, we need to think that x times 4, okay, let's think about this. X times 4 is going to be x plus 9. That makes sense? Small side times scale factor is x plus 9. So let's write it out. X plus 9, the side that we're trying to find, is going to be the original side, x multiplied by 4. So we've actually got the equation x plus 9 equals 4x. You can take 1x away from both sides, and that leaves you with 9 equals 3x. Divide through by 3, and we've got x equals 3. X equals 3 centimeters. So the idea is, when we started with the numbers bit, and it's easy to sometimes say we don't need to write stuff down, I can do it in my head. You can see here there are examples where we need to introduce a little bit of algebra in order to solve the problem. So hopefully you can use these examples to help you as you try these things out. Hope that makes sense and it's helpful to you.